So today I will give you a review for chapter 12, which talks about multiple access techniques. So what did we learn in this chapter? It's just a quick refreshment to what we studied and a quick summary to what we learned. We have studied many multiple access protocols in this chapter. These multiple access protocols can be divided into three main groups, which are random access protocols, including Aloha, carrier sensing multiple access, SYSMA ZD, SYSMA CA, and controlled access protocols, which include reservation and pooling. Then channelization protocols, which include FDMA, DDMA, and CDMA. So in the first group, random access protocols, transmission is random among the different stations. So there is no rule specify which station should send next. Whenever you have data, you will directly send through the link. In controlled access protocol, a station can't send unless it has been authorized by other station or centralized controller. So the centralized controller should give you first permission to start your transmission. In channelization protocols, there is the available bandwidth of a link is shared between different stations in time, in frequency, or through codes. So there is a specific bandwidth for each station to transmit. The bandwidth can be time, as in time division multiple access, or TDMA, can be frequency, as in frequency division multiple access, or FDMA, or can be a specific code. You can transmit all the time, all the frequency, but using a specific code. So just a quick summary here. In pure Aloha, we studied about different techniques in each group. So in the first group, random access protocols, we started by pure Aloha. In pure Aloha, each station sends a frame whenever it has a frame to send. And as we studied, pure Aloha vulnerable time equal to double the frame time or transmission time. And the vulnerable time is the length of time in which there is a possibility of collision. And the throughput for pure Aloha is J multiplied by exponential minus 2J, which as we see during the class, very low throughput. Pure Aloha maintains very low throughput. So in slotted Aloha, we divided the time into slots of T-frame and force the stations to send only at the beginning of the time slot. So by using this simple enhancement, the slotted Aloha vulnerable time becomes equal to T-frame and the throughput has been doubled. In carrier sensing multiple access, or SYSMA, it requires that each station first listen to the medium or check the state of the medium before sending. So unlike Aloha or pure Aloha, where a station can directly send, now in SYSMA, each station first listen to the medium before sending. So in SYSMA, we studied three methods to define what should the station do if the channel is busy or idle. So we listen and then decide to transmit or not, to transmit or wait for some random time. So we studied three different methods: one persistent, non-persistent, and p-persistent method, to see how a station can deal with a busy channel or idle channel. Then In SYSMA CD, present the algorithm to handle the collision. Now we need to detect the collision. So SYSMA CA try to detect the collision. In SYSMA CA was invented for the network, for the wireless network, where the collision are avoided. So in SYSMA CA, it's invented for the wireless network where we can't detect the collision due to inaccurate calculation of the signal level or energy level, so we can detect the collision accurately. So in SYSMA CA we need to avoid the collision through the use of interframe space, contentional window, and acknowledgements. Then in the second group, which is controlled access protocols or multiple access protocols, we studied reservation method, where a station needs to make a reservation before sending the data, and pooling protocol that work with topologies in which one device is designed as a primary station and other devices are secondary station, and all data exchanges must be made through the primary device. So in the pooling, we have primary device, all data exchange must be made through the primary device. So it's centralized controller. Then in the third group, channelization is a multiple access method in which the available bandwidth of the link is shared in time. So in this case, we will have TDMA in frequency. In this case, we will have FDMA, or through different codes. In this case, we will have CDMA. In CDMA, the codes are called orthogonal sequences or orthogonal codes or orthogonal chips. So each station should have an orthogonal code or orthogonal sequence. And these orthogonal sequences must have two properties. First, each sequence is made of n elements, where n is the number of the available stations. I need to give them codes. And second property, if we have multiple sequences and we multiply each two equal sequences, if we have equal sequences and multiply the sequence with itself, element by element, and add the result, we will get n. Well, the result will be equal to n. The inner product of two equal sequences is equal to n, where n is the number of stations. Also, in CDMA, to generate a chip sequence or codes, we use a Walsh table, which is a two-dimensional matrix with an equal number of rows and columns. Okay, so let's start it by some exercises. The first questions, let's practice with some questions. In the first question, in space, the chance of collision can be reduced if a station sends the medium before trying to use it. What a protocol sends the medium first? Yes, SYSMA, or carrier sensing multiple access, that supports sensing before sending. In space, the stations share the bandwidth of the channel in time. So we share the bandwidth, but in what? In time. So share in time. So we have TDMA. It's TDMA, time division multiple access. In the sequences are generated using orthogonal codes, such the Walsh table. So Walsh table, orthogonal codes. So we deal with CDMA, carrier division multiple access, TDMA. In the space method, after the station finds the line ideal, it sends its frame immediately. If the line is not ideal, it continuously senses the line until it finds it ideal. So we have two properties here. continuously sends the line, and once it's idle, it sends directly or immediately. So this is one persistent method, because we transmit immediately with a probability of 1 once the line is idle. In the space method, time is divided into intervals. In each interval, a reservation frame precedes the data frames sent in that interval. So we have a reservation, and we divided the intervals in time. So it is reservation. So remember, once you have a reservation mini slots, if you remember, we have reservation mini slot where each station say I need to reserve a slot to transmit in this reservation mini slot. So once you have a reservation frame, it's reservation protocol or reservation method. In space method, no station is superior to another station, and none is assigned the control of another. So it should be random access. No station is superior, no one is assigned control over another, anyone has the data can transmit, so it's random access methods. Other questions: to avoid collisions on wireless networks, who was invented? Avoid a collision, and also on wireless network. So it is SISMA CA with collision avoidance. In the method, the primary device controls the link. The secondary devices follow its instruction. So we have a primary and followers. So must be pooling or controlled access methods, specifically pooling, where we have primary device and secondary device. Next questions: in each station is forced to send only at the beginning of the time slot. Who forced you to send at the beginning of the time slot? Yes, slotted Aloha. Slotted Aloha, we divided the frame into slots or the time into slots, and each station should send only at the beginning of the time slot. In methods, the stations consult one another to find which station has the right to send. There is a central controller, or each station consult each other to find the best, to find when to send. So it is controlled access method. So in controlled access method, there is a centralized controller, or the stations consult a centralized controller, consult another station to find which station has the right to send. So it's controlled access. In pure Aloha, the vulnerable time is the frame transmission time. Pure Aloha, remember, it's 2 times. If it's slotted Aloha, it's equal to the frame transmission time. But in pure Aloha, the vulnerable time is double or 2 times the frame transmission. So take care of Aloha or slotted Aloha or pure Aloha. In methods, a station can't send unless it has been authorized by other stations. So there is another authorized station give you permission. So you have a central controller, so you can send without consult another station. So it is again controlled access. Once you have a station that give you authorization, give you permission to send, so you have a centralized controller, so it is controlled access. In a station monitors the medium after it sends a frame to see if the transmission was successful. If so, the transmission is finished. If, however, there is a collision, the frame is sent again. So which method send the frame, then see if the transmission was successful or not? So this method tries to do what? To detect the collision. So it transmits the data, it sends the frame, and try to detect if there is collision or not. So it is SYSMA CD, SYSMA with collision detection. I send the frame and I am trying to detect if there is a collision or not. Space is based on coding theory and uses sequences of number called chips. For sure, when you have coding or codes or chips or sequence number or sequence code, all this refers to CDMA. Okay? Another type of questions. In the blue figure, when can B detect the collision? This figure represents how collision can happen and how each station can detect and when each station can detect the collision. So try to focus on the timing frame here. Here we have in the vertical lines, it represents the time. So the gray area here represents the collision. B start to transmit in the yellow, and C start to transmit in blue, and once there is two frames at the same time, it's a collision. So the gray area here represents the collision. So T1 represents the start time of B to transmit. So at B will start to send at time T1. C will start to send at time T2. But when the collision happen and when can be detected? So at time T3, B start to see the gray area. So at time T3, B can detect the collision. Where C can detect it earlier. So C can detect the collision at time T4. And remember, T3 is greater than T4. So C will detect the collision first, then B will detect the collision at T3. So when can B detect the collision? Detected at T3 after C. So C will detect it first, then B can detect it according to this figure. Okay. Another question. What is the number of sequences needed, or what is the Walsh metric size? Because Walsh metric size represents the number of sequences that we can generate and use at each station. In case of using CDMA, for sure, because Walsh matrix and sequences, for sure it's CDMA. If we have 90 stations in our network, so if we have 90 stations, what will be the size of the Walsh matrix and the number of the available sequences that I can use? As we studied, Walsh matrix is square matrix, and the size of the Walsh matrix or the size of the generated sequences should be 2 to the power m. So should be of power 2. So if I need to support 90 stations, so at least I have to generate 2 to the power 7 codes or sequences. So at least I need to generate 128 codes. And then I will use 90 of them for the 90 stations, and the extra codes will be extra. But at least I should generate 2 to the power 7, 128. Because if I generated 2 to the power 6, it will be 64. So less than 90 stations. So at least I need to generate 2 to the power 7 to support all the 90 stations. Because again, the generated sequence or Walsh metric size should be of the power 2. Another last questions is a network using SYSMA CD has a bandwidth of 10 megabit per second if the maximum propagation time is 25.6 microsecond. What is the minimum size of the frame? Minimum size of the frame or any thing thing related to SYSMA CD, we have a clear rule. The frame transmission time is T frame equal to double propagation time. So T frame equal to double propagation time. So we can calculate T frame. And as we know, the frame transmission time equal to frame size divided by the bandwidth. So I can easily, I know the bandwidth, I know the frame transmission time double the propagation time, so I can calculate it, the minimum frame size easily. Also remember that if I don't give you the propagation delay, you can calculate it. I can give you the distance and the propagation speed, so you can calculate the propagation delay easily. Or if I give you the propagation delay and you calculated the frame transmission time, you can calculate the frame size, bandwidth, any other parameters. So from the propagation delay, for example, you can calculate distance given the propagation speed and so on. So we have here three main formula that control this type of questions. The frame transmission time, T frame, is double the propagation time. Frame transmission time equal to frame size divided by the bandwidth, and propagation delay equal to the distance divided by the propagation speed. This was the last question, and thank you.